Hi, I'm going to teach you a math lesson. 82, graphing the sine and cosine functions. You're going to need your graphing calculator today. You are going to want to have a copy of your unit circle today. I've got Desmos on my phone, your notes, and I'm going to send you some special graph paper today, or I'll put it in an envelope for you or whatever, but I'll send it to you. You can print some off at home if you'd like. Special trigonometry graph paper for sinusoids. Sinusoids. That's right. That's what we're going to do today. Alrighty then. Got a special kind of graph that wiggles up and down, and then it repeats itself over and over and over and over and over and over. So we have what's called a periodic function. What we're going to do is we're going to pull apart the unit circle. We're going to take some of the values on that circle and we're going to mark them out on a angle by value type of grid. You can do these on your calculator, but you're going to have to change your window a little bit. We're going to have to go zoom trig, and we also want to double check on our mode. A lot of the things I'm going to be doing today are going to be in radians because I want you thinking in radians. You can also do it in degrees just to give yourself an analogy there. But radians is kind of the way I want you thinking today. So when you go zoom trig today, it'll put it in radians, hopefully, if that's what your mode is set to. Okay, pulling apart the unit circle. First function that we're going to do today is going to be sine of the angle. And I wrote this in function form. So this means that our argument is going to be, let's plug in an angle. And then our output is going to be, what's the sine value for that angle? So as you can see, that is something that we're doing off of our unit circle, except all that we care about is the second part of all those addresses today. We're going to input the angles in radians, like 0 and pi over 6 and pi over 4 and pi over 3 and pi over 2. We're going to go around the circle. We're going to say if I plug in that particular angle, what is the y value that pops out? Okay? Now, we know already that the y values vary from 0 all the way up to 1 here at the top of the unit circle, and then it becomes 0 again once we're over here at pi radians, and then it's down here to -1. So we know that the biggest that the y values get is 1, and the smallest that the y values get is -1. So on my little graph here, on this scale here, the sine of the angle, the value that pops out when I plug in the angle, I've got 1 up here at the top, and I've got -1 down here at the bottom. That's as far as those values can go. And then you get everything in between, like square root of 3 over 2, and 1/2, and square root of 2 over 2, and negative square root of 3 over 2. They're all bound between 1 and -1. On this axis, I've put the angles. 0, and I've shoved in there pi on 6, pi on 4, pi on 3, then pi over 2, pi, 3 pi over 2, and 2 pi. And then I haven't gone any further than that because the pattern just repeats itself. So you'll get everything you need to know in this first 2 pi radians, or one time around the circle, right? If you go another time around the circle, you get the exact same pattern, or 3 times. Or if you go backwards around the circle, that picture will just extend in the negative direction, the negative angle direction. So this is all I need. From 0 to 2 pi, or from, if you'd like, 0 to 360 degrees. But the arrow keeps going this way. So I've got the angles in radians or in degrees up here on top. And then on the y-axis, I've got the sine values from 1 to -1. And if we go around our unit circle and we just only look at the y values, only look at the sine values going around the circle, we see that over here we have that the sine of 0 is 1. Sine of 0 radians, is 0. So I put a dot right here to represent that, Anyway, we're thinking about the height on the unit circle when we're thinking about the sine values. If I go all the way up to 90 degrees, sine is 1, so I put a dot up here at 1. And then at pi, I have 0 again. At 3 pi over 2 at the bottom of the unit circle, I have 270 degrees, a negative 1. And then when I get to 360, or 2 pi radians, I'm back to 0. Now I could put in some of these in-betweens here. Let me put for myself a 1/2. At pi over 6, the value is 1/2. At pi over 4, the value is square root of 2 over 2. It's about 0.707. And when I'm at pi over 3, or 60 degrees, I'm at 3 pi over 2, which is about 0.866. So that's what I get. I know that it's also symmetrical on this side, that I'd have a pi over negative square root of 3 over 2. I'm going to have a square root of 2 over 2, and I'm going to have a 1/2 in there. Okay? Now I put those in there, like the first two quadrants, the y values, or the sine values for the first two quadrants, just so I can get an idea of what the shape of this thing is. It doesn't go like straight lines. It's curved. Oops, I'm not going to hit that one. There we go. And it's going to curve down, and it's going to curve back up. And that's kind of a wonky version of it, but if I graphed it on my phone, this is what I get. Or if you did it on your calculator, and you went in there and you plugged in sine of x is what we have to do here, and then I'm going to go zoom 7 for zoom trig, and this is what I get. Now my picture up there really only goes from 0 to 360, or 0 to 2 pi, so I'm going to go into my window and change my x minimum to 0. I'm going to keep everything else the same. Scales are by pi over 2's, but that's what I get. Wiggle up, wiggle down, comes back, crosses the line again. Got a little bit of terminology for the different parts here. Then any function that wibble wobbles and just repeats itself is called a periodic function. As over a certain period of time or a certain period of distance, you're going to have a repeating pattern. So it's kind of interesting that we call it the unit circle, because circles just go around and around and around. We care about the wavelength if we're talking about sound, or we're talking about energy, vibrations, things like that could be modeled with this. So we care about how long this is. If this wasn't just degrees, if this was some other unit, like maybe we're thinking about the radius. Put a point on a wheel, and then how high or low it is from the center. So we're looking at this, and we're like, there's one full wave, okay? Now, the amount of time that it would take for that to go through, like how long would it take for that wheel to go around once, that would be called its period. Its period. So we're concerned about that. We're concerned about what's the length of the angles, what's the angle that we have to go through to get back to where we started from in the same direction that we were going. We're also going to have amplitude and frequency. Amplitude will measure how far away from our center line the graph goes, and frequency will say how often do these waves come. Okay, how often or how frequently in a given amount of time, like an hour or a minute, or how many times a second does one of these waves get done, and then repeat it. So think ocean waves or sound waves or spring waves or anything like that. I've drawn a kind of an interesting picture, at least for sine, that I'll show you here. I've got the unit circle superimposed on a graph showing the angles. So I'll just show it to you here. So I'm talking about this set of pictures right here. And so I've got the sine of 0, 90, 180, 270, and 360, and I show you their positions on the unit circle, and then how that relates to making a sine curve. Since we are only tracking out the y values, which is the height of the dot on the circle. It seems to make some sense. So that's sine. We start with sine because sine starts at 0, goes up to 1 pretty quickly, comes down again to 0, -1, 1. Okay? That starting at 0 with the line right there, sine starts at 0. You know that from the position 1, 0 at 0 degrees or 0 radians. I'm going to redo this. We're going to do cosine now. Okay, you ready for cosine? And we know that the values of cosines only go from 1 to -1 as well. But now we're going to look at the x values around the unit circle. Maybe I'll put these first 3 in just because, right? Square root of 3 over 2, comma, square root of 2 over 2, comma, and 1/2, comma. I don't really care about the other ones because I'm only concerned about the cosine values associated with each angle. Okay, so we're going to go from 0 to pi over 2, pi, 3 pi over 2, to 2 pi, so we can go around the circle 1 time. So, at our starting place, the cosine's value is 1. And then when we're at the top of the circle, it is decreased to 0. And then when it gets over here, its value is -1. When we get down here to 270 degrees, or 3 pi over 2, its value is back to 0. And when we get to 2 pi, it's back to 1. If I want to put in some of those extra values, we could do that. Put pi on 4 right here. That's 45 degrees. We see that it's square root of 2 over 2, which is about 0.707. If I was at pi on 6, it's square root of 3 over 2, so that would be right about there. And at pi on 3, it's 1/2, right about there. So we follow the curve. And that's what one cycle of cosine looks like, which you could go ahead and do on your graphing calculator. But cosine starts high. Cosine starts at 1. Sine started at 0. It follows the same pattern, and it would just keep going. But this looks a little bit different because we're taking a slice of this periodic function, which if we kept going would just do this. We're taking it from this position to this position, so it's got like starts on a hill, it goes down, it comes back up like a, I don't know, like a skateboard, half pipe type of thing. Whereby sine started here and came up and came down, down, and back up. They're what's called 90 degrees out of phase. If I took this one and I shifted it over 90 degrees, it would superimpose onto the other one. So that's cosine. The cosine function, if we're just tracing out the x values as we go around the unit circle, comparing their angles to their values. Angles to values. Okay, that's the basics of it. And again, I did that in radians. But we can do a lot of stuff except for just the sine of theta. And we know that there's an imaginary 1 in front of both of these functions, right? 1 times sine theta and 1 times cosine theta. So there's a bit of fiddling around we can do with these functions to change what they look like. And we had over here that we were going to change an amplitude. We're going to fiddle around with amplitude. Amplitude on one of these graphs is the distance that the picture will vary from its center line. Okay, and so it's the same distance either vertically or up or down here on the thing. So when we go to figure out amplitude, amplitude is adjusted by changing this number that's in the front. I mean, if we were going to make this taller and go up to 2 and down to -2, all we'd have to do is take every value that we had for starters maybe this one's down to -1 and to 1. And we're going to double it. So it stretches it this way, but it's not going to change some of these other things. It's only going to change its vertical aspect. So if I change this to 2, I guess this is sine. If I change this to 2, it'll go twice as high as it went the first time. Its peak will be at 2 rather than at 1. And you can reduce it to 1/2 and you get a smaller one like this. So you're changing basically this height from the center to either the peak or the valley. That's what the amplitude is. And the amplitude will be adjusted by changing the number in the front of the function. How far from the midline? Period determines the horizontal distance to get back to the same position in the same direction. The period is adjusted. The number of waves, really, that's adjusted is going to happen over here. Let's just take this sine, okay? And if I went like this, and maybe I should put an x there because that's what you're going to get when you got your do it on your calculators. 2 sine of 2x. Now the 2 here actually is adjusting the frequency. If you would like more waves to come by in a given amount of time, if you want twice as many waves to come by in the same amount of space, let's say again that this goes out to 2 pi radians, goes through 1 full cycle. If I adjust this, now it's going to, I'm going to get twice as many waves in the same amount of space if I adjust this number right there. To me, that's easier to figure out by putting a number there than some of the other mumbo jumbo that they'll list for you. But for normal sine and cosine functions, the period, if you don't adjust anything, is 2 pi radians or 360 degrees. Now I just cut that period in half. Okay, so for 2 sine 2x, I just reduced it. I made it twice as frequent, so the period is now 2 pi divided by that number right there. The period is only pi radians. I go through pi radians, I've gone through a cycle. I do the next pi radians, I've gone through 2 cycles altogether. So that number right there adjusts the frequency. And then there's a relationship between the period and the frequency. They're like reciprocals of each other. If I double the number of waves, I've halved the period of that function. Okay, so I'll give you some little rules here to follow. But you can play around with this. You can see for yourself what happens if I make it negative. I go -3 sine x, what that would look like. What changes when I make that number negative rather than positive. It would be a good idea to always kind of have somewhere on there just your normal 1 times sine x so you can see the original and then what changes about it. But I would invite you to fiddle with these numbers and see what happens. And then again, you can fiddle with putting 2x or 3x or maybe 1/3 x and see how that adjusts things this way. So the number in front adjusts the picture this way, and the number inside the parentheses is going to adjust things this way. That would make sense, right? It's almost as if I'm taking my y value over some number equals my sine value with something being adjusted next to the x. This is basically the same thing as that. There you go. So the -3 adjusts the y stuff, and the other 3, or the 1/3 here, would adjust the x version of stuff. So let me summarize that really quickly here. Let me clear the board, and I'll summarize that for you. You ready? There we go. For either the sine or the cosine function, for a times sine bx, or if we use cosine, they're the same shape, but just a little bit shifted off from each other. Y equals a cosine bx. We're going to determine the amplitude by taking the absolute value of the number a. Absolute value because amplitude just says how high or high low. how low. If it's negative, it still has the same amplitude. We're going to take the absolute value. You want to know the frequency over one cycle or over 2 pi radians. You're going to use the value b. And then to calculate the period, you're going to go 2 pi, which is our regular frequency, divided by, or regular period, I should say, divided by b, how many times that graph occurs over 2 pi radians of angles. You could also put in here 360 degrees. How many times does it happen over 360 degrees? Amplitude, frequency, period. We use the frequency to calculate the period. Amplitude and period are the most important parts. So if I'm going to draw a picture by hand, which you can do that, or you can use that magic paper that I gave you, though the magic paper only has certain points on it. Let's take up an example, I don't know, I'll take -2 sine 3x. Okay, I'm going to just start with that. And then first I'm going to determine the amplitude. The amplitude is the absolute value of -2. So the amplitude is 2. It's going to go up to 2. It's going to go down to -2. So now I've labeled that axis there. I'm going to say this is the angle, and this is the sine of the angle. This is the function. So that's the value that pops in. Second, determine the period. Well, normal period is 2 pi. The period is determined by taking 2 pi divided by b, and b is 3. So the period is 2 pi over 3. Okay, so at 2 pi over 3, I've gone through one full cycle. All right? I've gone through one full cycle. Number 3, divide the period into fourths. There's into half. There's into fourths. Just like I had before, it takes our normal 2 pi and it squished it down so that that's all that we get to see. Use A to determine the pattern. Okay, so this is sine. Where's sine start? Sine starts right here. And then it went up, back to the middle, down, and then finished. All right? Those are going to be the values, or that's the shape of the thing. Oh, it's -2. So actually, you can switch these. It goes down first, and then up, and then back to the middle, because it's flipped upside down. And then plot the 5 critical points and connect them. All right, there's 1, 2, 3, 4, 5. And if you did that on regular paper, you would just, if you had 2 pi here and you had pi there, this one only goes to 2/3 pi, so you get your full cycle like that. Okay? If you're using the regular paper that I'm sending to you, you'd have to adjust it. I kind of think it just makes more sense if you're going to draw it by hand, or you're going to put it in your calculator and you're going to try to represent what you're able to do there. But follow our little 5-step thing, and you can draw any of these equations by hand. They're only going to give you a different number here and maybe a different number there, and that's enough to draw what this thing looks like in general. Play around with it though. Change those numbers and see what happens, and you'll get a hang of it pretty quickly as to how to go about adjusting things on that. Anyway, I'll send you that magic paper, and if you need some help, you can go ahead and give me a call.